Today I discuss on important topics related to inner product space. We also known about that bilinear forms. Okay, bilinear forms also known about. Today we discuss this one. Okay, this one obviously one important topics related to inner product space. We start from definition. Okay, so write it in this way. Let V be a vector space. Okay, vector space over a field F. Over a field F. Okay, then what happened? A function h from the set okay, V cross V of order pair of vector of order pair of vectors, okay, of order pair of vectors to F is called a bilinear form. Is called a bilinear form. Okay, on V, if H is linear, okay, in each variable, okay, when the other variable is held fixed, when the other variable is held fixed, okay, that is what, that is, okay, H is bilinear form on P, that is H is bilinear form on P, okay, if first one here H of ax1 plus x2 here y equal to a of h x1 y plus h x2 y, okay, for all x1 x2 xy, for all x1 x2 y belongs to V and A belongs to F, and A belongs to F, okay, and here second option, okay, H of x a y1 plus y2 equal to a h x y1 plus h x y2, okay, for all here x y1 y2 belongs to V, x y1 y2 belongs to V, okay, and A belongs to F. Understood? Then what happened? We now erase that portion and going to discussion of that. The set of all bilinears from on V by the set of all bilinear from on V by what? B of V. Understood? Observe that an inner product on a vector space is a bilinear form if the underlying field is real, but not if the underlying field is complex. Okay, now we write it in this way. Observe that, okay, observe that an inner product on a vector space, okay, is a bilinear form, okay, if the underlying field is real, but not if the underlying field is complex. Okay, so now we also give some example related to that topics. Okay, so now erase that portion and going to discussion some example related to that topics. Here we write example. Okay, define a function h r square cross r square to r by here h of a1 a2, okay, b1 b2 equal to what? Equal to 2a1 b1 plus 3a1 b2 plus 4a2 b1 here minus a2 b2, okay, for a1 a2 and b1 b2 belongs to r square. Okay, now we could directly verify that h is a bilinear form on r square. This one is easy, that means so h is a bilinear form on r square. Okay, not a problem at all. Then what happened? That means how we related this one. Okay, we also write it a equal to 2 3 4 minus 1, okay, and here x equal to a1 a2, okay, and y equal to what? Y equal to b1 b2 and y equal to b1 b2. Then what happened? Then h of x y equal to what? X transpose ay. Okay, the bilinearity of h now follows directly from the distributive property of matrix multiplication over matrix addition. Okay, then this one, in this way we also represent as xy. Okay, now we give another example related to that. Okay, so we also write another one. The bilinearity of h now follows from directly from distributive property of matrix multiplication over matrix addition. Okay, the bilinearity of h, okay, now follows directly from the distributive property, from the distributive property of matrix multiplication, property of matrix multiplication over matrix addition, over matrix addition. Understood? Now we also discuss another example related to that topics. Okay, so now we erase that portion and going to further discussion of that. Here example 2. Okay, let V equal to Fn, where the vectors are considered as column vector. Okay, where the vectors are considered as column vectors. Okay, then what happen? For any A belongs to, for any A belongs to Mn cross n A, what happen? Define H V cross V to A by, okay, Hxy equal to X transpose Ay. Okay, for xy belongs to V. Then what happened? Xy are n cross 1, x and y are n cross 1 matrices. Okay, and A is an n cross n matrix. A is an n cross n matrix. Okay, then Hxy equal to what? Hxy is a 1 cross 1 matrix. We identify this matrix with its single entry. Okay, then what happened is here we write it in this way. That means here for A belongs to A. Okay, for A belongs to A and x1 x2 y belongs to V. We have what? We have h of ax1 plus x2 here y equal to what? Equal to ax1 plus x2 transpose ay equal to what? Equal to ax1 transpose plus x2 transpose ay equal to what? Equal to ax1 transpose ay plus x2 transpose ay equal to what? Equal to ah x1y plus here h x2y. Okay, in this way we also discuss this one, HP linear. Okay, then what happened? HP linear. Linear with respect to what? With respect to, that means first variable x. Okay, with respect to x. Now we also in this way discuss similarly. That means h of here h of x a y1 plus y2 equal to what? If equal to x transpose a y1 plus y2, understood? Then here x transpose a y1, here a plus here x transpose a y2. Okay, then what happened? Then a of hx y1 plus hx y2, understood? Then what happened? So we write it hb linear with respect to y. Okay, then what happened is here, then we also discuss a, so this one is, we write it in this way, hp bilinear. Okay, then now we also write some following result related to that topics. We erase that portion. Okay, for any bilinear form, for any bilinear form, okay, for any bilinear form H on a vector space, okay, on a vector space V over a field F, V over a field F, okay, the following properties hold. The following properties hold. Okay, for any bilinear form H on a vector space V over the field F, the following properties hold. Understood? First one, we marked it 1. If for any x belongs to, if for any x belongs to V, okay, the functions Lx, the functions Lx such that Lx and Rx such that V to L, okay, are defined by what? Here we write it in this way, Lxy equal to hxy and rxy equal to hyx, okay, for all y belongs to V. Understood? Then Lx and Rx, then Lx and Rx are linear, okay, not a problem at all. Next we write it in this way, here h of 0x equal to h of x0 equal to 0, okay, for all x belongs to V, for all x belongs to V. Third, here for all x, y, z, w belongs to V, what happened? H of x plus y, z plus w equal to what? H of x, z plus h of x, w plus h of y, z plus h of y, w. Okay, Now next, number 4. Okay, if J here V cross V2 if is defined by okay Jxy equal to Hyx, understood? Then J is a bilinear form. Okay, then J is a bilinear form. Okay, now we erase that portion and going to further discussion of that. Okay, that means we also discuss one definition now. So we erase that portion and going to discussion one definition. Let V be a vector space. Okay, let H1 H2 be bilinear forms on V. Let H1 and H2 be bilinear forms on V. Okay, and let A be a scalar, and let A be a scalar. Okay, then what happened? Then we define the sum. We define the sum. Okay, here H1 plus H2 and the scalar product and the scalar product. Okay, AH1 by the equations. Here H1 plus H2 xy equal to H1 xy plus H2 xy and AH1 xy equal to, in this way, A of H1 xy equal to what? Equal to A of A here H1 xy. Okay, that means for all xy belongs to V. In this way, we also defined H1, H2 and AH1. Understood? Now we are going to discussion one theorem related to that topics. Okay. Then we write it here one theorem. Okay. For any vector space, V, the sum of two bilinear forms, okay, and the product of a scalar and a bilinear form of a scalar and a bilinear form, okay, on V are again bilinear form, bilinear forms on V. Understood? Then furthermore BV is a vector space with respect to these operations. With respect to these operations. Okay, BV is a vector space with respect to this operation. That means one addition, okay, sum and scalar product of bilinear forms. Okay, so sum of two bilinear forms and products of a scalar and a bilinear form on V are again bilinear form. Then BV equal to the set of all bilinears from on V is the set of all bilinears from of V on V is a vector space with respect to these operations. Understood? Now we also going to discussion another definition. Okay, so we now erase that portion and going to further discussion of that. Okay, let beta v1 v2 vn be an order basis. Let beta here v1 v2 vn, okay, be an order basis, okay, for an n-dimensional vector space, for an n-dimensional vector space. Okay, V vector space V, beta be an order basis for an n-dimensional vector space. Okay, V. Then what happened? And let H belongs to BV. Okay, we can associate with H and n cross n matrix A. We can associate with H, okay, and n cross n matrix A. Whose entry in row I, and column C is defined by Aij equal to H Vi Vj. Okay, for Ij equal to 1 2 n. Understood? That means we also discuss H and n cross n matrix A whose entry in row I and column J is defined by Aij where H Vi Vj. Okay, then we write this definition. That means the matrix A above is called the matrix A above is called the matrix representation of representation of H with respect to with respect to the order basis beta. Okay, with respect to the order basis beta, and it is denoted by psi beta h. Understood? The matrix A above is called the matrix representation of H with respect to the order basis beta, denoted by psi beta H. Okay. Now we are also going to discuss one example related to that. Okay. So we write it in this way. That means psi beta is a mapping from what? From BV to, okay, the set of all bilinear forms on V to M n cross n F. Understood? Then what if the field of scalar for V, and that takes a bilinear form H into matrix representation of phi b H. Okay. So now we give example. We erase that portion and going to discuss some example here. Okay. So we write here example. That means we consider the bilinear from this one, H equal to here R square cross R square to R by, in this way, H of A1, A2, B1, B2 equal to what? 2A1, B1, 3A1, B2 plus here 4A2B1 difference A2B2. Understood? Here for A1, A2 and B1, B2 belongs to R square. Okay. Then what happen is here we write it in this way, beta equal to, okay, 1 1 and 1 minus 1, okay, and b equal to psi beta h. Understood? Then what happened? Then b of 1 1 equal to what? H of 1 1 here 1 1. Understood? Then this one equal to what? 2 plus 3 plus 4 difference 1 equal to 8. Understood? That means H of 1 1 1 1 equal to 2 plus 3 plus 4 difference 1, then 8. Here B of 1 2 equal to what? H of, okay, 1 1 and here 1 minus 1. Understood? Then this one equal to what? This one equal to 2 minus 3 plus 4 plus 1 equal to 4. Okay. And here B of 2 1 equal to what? H of 1 1, sorry, 1 minus 1 and 1 1 equal to what? Equal to 2 plus 3 difference 4 plus 1 equal to 2. Okay. And then what happened? Then B of 2 2 equal to, okay, then B of 2 2 equal to here H of 1 minus 1 1 minus 1 equal to what? Equal to 2 minus 3 minus 4 minus 1. Okay. Then minus 6. then so psi beta is equal to, in this way we write it 8 4 2 minus 6. Understood? So in this way we also represent the matrix representation of age. Okay, some bilinear form age. Okay, with respect to some order basis beta. Okay, so in this way we also represent this one is the matrix representation. Okay, representation of age with respect to beta. Okay, understood? Then today I stop here. If you get this type of video, please subscribe my channel. If you have any questions, comment, suggestions, write it in comment box. If you want to give like, please click on like options. So today I stop here. Thank you.